Hi, welcome back to my channel, and for today's video, we will be continuing with the installment video of the linear dependence and the span of a vector space. So this time, we will be talking about the basis of a vector space. For those who are new to my channel, please don't forget to subscribe there so that you'll be updated on a lot of videos that I'll be uploading soon. So today, we will be talking about the basis of a vector space. Okay, so let's start with the definition. So we have here, given that V is a vector space over a field F, so a subset B of V is called a basis for V if number one, it is linearly independent over F, and it is a spanning set for V. So let's consider this for example. So you have Fn here, and let EI be the n tuple with 1 in the ith position and 0 for all positions that j is not equal to I. So if you're going to take the set here, E1, E2 up until En, then this set here is a basis for a vector space Fn. And in fact, this is called a standard basis for Fn. Why? This is pretty obvious. You can take this as a linear. This is actually a linear combination of the vectors coming from Fn. So that's it. Similarly, aside from being qualified to have a linear combinations of the vectors coming from Fn, this actually is a spanning set. Here, let's consider another example, number 2. So given that you have B be the set containing vectors B1, B2, and B3, where these vectors are these, then we're going to check if this is really a basis for the vector space R3. So we're going to check if B is a basis for R3. So I'm gonna take a question mark for that yet. Okay, observe that we have shown this already on the previous video that these vectors are actually example from the previous video that this already is a set that is linearly independent over R. So here, so that means condition 1 is already satisfied. So let's check if condition 2 is satisfied here. Note that if we let the vector xyz coming from the R3, then what we're going to show is we wish to show a solution satisfying this linear combination. Let's gonna have let's say we have C1, C2, C3, and it's coming from R. So we have C1 V1 plus C2 V2 plus C3 B3. This is equal to XYZ. Now your C1, your C2, and your C3 are scalars from R. Okay, so by virtue of this, C1 plus 2C2, I'm sorry, it should be C2 equals X. C1 minus C2 minus 4C3, this is equal to Y. And negative 2C1 plus C2 plus C3 equals Z. So how did I get these systems of linear equations? This is simply a manipulation over the fact that C1 here we have a scalar multiplication to the vector V1. So I would have C1, C1, negative C1 plus another vector here. The C2 here can have C2 V2 is 2C2 minus 2C minus C2, then C1. Then this vector is 0, negative 4 C3 then C3. So that's why if I'm gonna have to add them all, then I would get a systems of linear equations here. So if you have any questions or clarifications, how did I get this? Because I am aware that I made shortcut assuming that you already have learned from the previous video about the linear combination and stuff like that. Then you can comment down there so that we will be able to discuss it thoroughly. Okay, now for that, you have the systems of linear equation. So what would I have to do with this? Remember that, observe that if this, assuming this is the first equation, this is the second equation, and this is the third equation. So if I'm gonna subtract the second equation from the first here, and then adding twice the first to the third, I would have C1 plus 2C2 equals X. So this is a new set of equations. I would get 3C2 plus 4C3 equals X minus Y. And I would get 5C2 plus C3 equals 2X plus Z. Now, this is pretty obvious here, this new set of equations. This is pretty obvious because we can do the manipulation here by solving simultaneous equations. Finally, I would get this, so I'm gonna move it here. I would get this C1 equals 10x minus y minus 4z. So this is just basic algebra we're doing here in this time. And this is C2 equals 7x plus y plus 4z over 17. And finally, I would get C3 here. That's negative x minus 5y minus 3z over 17 here. Then this is already here scalars. These are scalars here. And so therefore B spans R3. So we can conclude that B spans R3, and which in fact B is a basis for R3. So therefore this is true. Always remember that the basis of a vector space is not unique here, because if you can see, you can just do a manipulation here, and you will take another value for C1, another value for C2, another value for C3, depending on what method you are actually doing here. Okay, so another example here, the set of monomials, the set here is actually a basis for a vector space with the space containing polynomials of degree less than or equal to n, together with a zero polynomial. Because of course this one here, that's equivalent to just 1 t to the 0, and that's technically 1. And these inside here are actually considered as vectors, so that's pretty obvious here. That's it. Okay, so given that a field of complex number C is a vector space over R, we're gonna check if the set I is a basis for C over R. So we're gonna check that. So I'm gonna take a question mark on this since we haven't proven that yet. Now let's check. This set containing 1i, observe that if a vector v in C coming from this set of complex numbers, then I can write v equals a plus bi, where a, b are in R, of course. I is your imaginary number. Observe that I can write this as a I times 1 plus b times I. So technically, this 1 here and this I here are coming from this set. So therefore, it simply tells us that the set 1i spans C. Okay, so condition 2 is satisfied. So let's check if the first condition is satisfied. Let's say if this set is a linear combination of the vectors coming from C. So observe that if x plus yi equals 0, remember your x and y are coming from R, then the equality, so if this is actually 0, then the equality for C, we have x equals y equals 0. Okay, so meaning to say that these are 0, and so the set 1i is a linear combination already of C over R. And so we can simply conclude that this is a basis for C over the space R. That's it. Okay, so now that we have done, we've shown already the examples for the basis of a vector space. So this time we will be considering the theoretical combination of the basis of a vector space, the linearly independent set of vectors, and um, the span of a vector space. So this time we will have a definition here. Consider that your X is a subset of a vector space V over a field F. So we say that X is a maximal linearly independent set if your X here, okay, given that your X here is linearly independent set, and you cannot find any other set greater than X that is also linearly independent. So this time X is already linearly independent. Okay. Similarly, if your X is a minimal spanning set for V, if your X spans V, this is minimal in the sense that you cannot find any other set less than X. I mean, any other set that can be a subset of the X that is also a spanning set for V. So this X already is the smallest of the cardinal of set in terms of set cardinality that is already a spanning set for V. That's it. So by that we will consider a theorem for the this definition. So we have this theorem here. Let X be a finite subset of a vector space V over a field F. So the following conditions on X are equivalent. So your X is a maximal linearly independent set, and then X is a maximal spanning set for V, and X is a basis for V. So to make this equivalent, I'm gonna show 1 implies if and only if 3, and 2 if and only if 3. So if I will be able to show this, of course, this one will be if and only if 2. Okay, so let's start with the idea of proving that 1 if and only if 3. So I'm gonna show here this proof. So if X is a maximal linearly independent set, so what could that be? So I'm assuming that X is the set x1 up to xn. So again, this is maximal linearly independent set. Okay, what does it mean? The non-zero vector v in v. So if you have v in v, so this is non-zero vector. If you add this v to the set x, so let's say x union the set containing v, then this is already linearly dependent, right? Because already, of course, v is already maximal. So if you're gonna add that, then that's not already the x. So remember, x is already maximal linearly independent set. So if you're gonna add another element, so you're not anymore taking that as an x. It's something else, and that's greater than x. And so it's greater than x, so that's pretty sure that's linearly dependent. So since this set here now, so I'm gonna call this set as, let's say, for simplicity, I'm gonna call this set as y. So this means that this y, there exists a linear combination. Of course, there exists a linear combination of vectors in y equal to 0 vector. So that is you're having a1, a2 up until an, and of course you have an plus 1, and because you're actually adding a vector on that, and these are element in F, not all zero, such that if you're getting the linear combination of these, so you have, I'm sorry, these are not vectors, by the way. These are scalars. So I'm gonna have an xn plus an plus 1 xn plus 1. However, this is v in this case. This is equal to 0 vector. Okay. Now, what does it imply? If an plus 1 is 0, then you would get this here, ax1 up until anxn. So in this case, your this is now the equivalent of your previous equation. So since remember that your x originally is linearly independent set, so this implies that your a1, your a2 up until your an are 0. This is a contradiction because the set already, when you add this v here, is linearly dependent. So one of these guys here must not be equal to 0. So this is already a contradiction. And so we are forced to say that an plus 1 must not be 0. And so an plus 1 must not be 0. Then I can write this, remember that the vector corresponds to an plus 1 is v. So I can write v as a linear combination of the others. So I would have a1 over an plus 1. And that's x1. I'm sorry, that should be x1 minus negative an over an plus 1 xn. So in this case, this v is a linear combination of the other vectors in x. So we have shown this on the previous example that if a set is a linearly dependent set over a vector space, then that's technically one of the vectors can be written as a linear combination of the other. So in this case, I write v here as a linear combination of the other vectors. So this simply tells us that x is a basis for v, because the vectors in x here, these all guys here are actually coming corresponds to the vectors in x, and they are actually written as a linear combinations of the vectors, and that vectors v is coming from v. That's it. Okay, so this time we will show 3 implies 1. So we already have shown 1 implies 3. So let's say if it works with 3 implies 1. So in this case, x is a basis for v, then we'll show that x is a maximal linearly independent set. So if x is a basis for v, so x is a basis for v, what does it mean? So if it's a basis for v, then every vectors in v, every vector in v is a linear combination, of course, of elements of vectors in x. So if we include, so if including another vector to x, then it might imply that x is linearly dependent set. I mean, the new set formed by including another vector is linearly dependent. So this simply tells us that x is a maximal linearly independent set. That's it. Let's show if 2 implies 3 here. So this time we will have to show that if x is a maximal spanning minimal, so it should be minimal here. Sorry. So it should be minimal here. So I apologize. It should be minimal. So if X is a minimal spanning set for V, then X is a basis for V. So let's show that number 2 holds. Then if number 2 holds, then there is no element of X. So no element of X is a linear combination of the others. Okay, so why? Because if there is an element in X that can be a linear combination of the others, then X will have a proper subset spanning the same subspace spanned by X. That is a contradiction to the definition. So since no element of X is a linear combination of the others, then X is already a linearly independent set. So hence, this is already a basis for V. So let's try if we start with number 3 and then goes to number 2. If X is a basis for V, then this is already a basis. Then of course no element of X. So no element of X is a linear combination of the others. So by that, this simply tells us that there is no proper subset that can span the V. So by the definition, X is a maximal spanning set for V. That's it. So we have shown already the proof of this entire theorem. So if you have questions or clarifications, don't hesitate to comment down there so that we will be able to discuss everything. And so we're good to go to continue with the next video. Okay, so we have one final theorem here. Given that if you have B containing vectors v1 to vn as a basis for V, then every element of V has a unique expression as a linear combination of elements of V. So our goal here is to show the uniqueness of a linear combination. Now, to show on that, I'm going to show the outline instead. So I have V coming from V. Observe that our B here is a basis for V, and so it's a basis, so it spans V. So B spans V. What does it entail? It simply tells us that the vector V has an expression as a linear combination of elements of B. Now, since V has an expression of a linear combination of elements of B, then I would assume another scalars here. So I will assume that there can be another linear combination. So I'm gonna assume sets of scalars. So I have A1, A2 up until AN. And I would also have another set of scalars, which is B1, B2 up until Bn. So in this case, I have V equals A1, V1 plus up until AN, Vn. And remember that A1, V1 plus up until AN, Vn, these guys here are actually equal to V. And I can write another B1, V1 up until Bn, Vn. So in this case, I assume that V can be written as another linear combination. And so they are equal to V. And so I can equate this here, these two guys here. So by equating these two guys here, I can do the basic algebraic manipulation. And so I would end up having this equation. A1 minus B1, V1 plus up until AN minus VN, and that's, I'm sorry, BN, VN, and that's zero vector. So everything on the right side, I transferred it to the left side, so I left with a zero vector on the right side. And so I would have gotten this one here. But take note that VI's here, these vectors VI's are coming from B. Remember that B is a basis for V. And so B is linearly independent set. And so, since this is linearly independent set, all scalars associated to the vectors coming from B are 0, which simply tells us that A1 minus B1 is 0 up until AN minus BN are 0. Meaning to say that all AIs are equal to BI for all I. So, we have shown the uniqueness of a linear combinations of elements from B. That's it. Okay, so that's all for now. Thank you so much for watching. So if you have, again, questions, clarifications, don't forget to comment down there so that we will be able to discuss that and to clarify things out. For those who are new to my channel, please don't forget to subscribe to my channel so that you'll be updated on a lot of videos that I'll be uploading soon. So thank you and have a great day.